We've all felt it. The pull that brings us back down to Earth after a jump. The force that keeps our feet planted firmly on the ground. Gravity. But what exactly is this invisible force? Isaac Newton gave us our first real glimpse into gravity. He observed that objects with mass attract each other. This attraction wasn't limited to apples falling from trees. It extended to the moon orbiting the Earth and planets revolving around the sun. His law of universal gravitation provided a mathematical explanation. Einstein, in the early 20th century, offered a radical new perspective on gravity. He proposed that gravity is a consequence of the curvature of space-time itself. Massive objects warp space-time, creating what we experience as gravity. Now you might be thinking, if gravity is just the curvature of space-time, is it even a real force? The answer is a resounding yes. Gravity, though arising from the geometry of space-time, manifests as a very real force, influencing the motion of objects and shaping the universe around us. Consider the feeling of weight you experience. It's the force of gravity pulling you towards the Earth's center, or the moon orbiting the Earth, held in its path by Earth's gravitational pull. These are tangible effects of gravity, undeniable evidence of its existence as a force. The Earth and the moon provide a captivating example of gravity in action. The moon, our celestial neighbor, is locked in an intricate dance with Earth, a dance orchestrated by the invisible force of gravity. The moon's gravity tugs on the Earth, causing the tides we observe in our oceans. The Earth's gravity, in turn, keeps the moon in orbit, preventing it from flying off into space. This gravitational interplay isn't limited to the Earth-Moon system, it's a universal phenomenon. Every planet in our solar system is held in its orbit around the sun by gravity. Galaxies, vast collections of stars, are held together by the combined gravitational pull of their constituent stars, gas and dust. Gravity, however, isn't alone in its role as a shaper of the universe. There are other fundamental forces at play, forces that govern the interactions of matter and energy. These forces, along with gravity, are the master architects of our cosmos, dictating how particles interact and influencing the evolution of the universe itself. We have the strong force, responsible for binding protons and neutrons together in the nuclei of atoms. It's the strongest of all the fundamental forces, but it operates over extremely short distances, primarily within atomic nuclei. Then there's the weak force, responsible for certain types of radioactive decay. And finally, we have electromagnetism, the force that governs the interactions between electrically charged particles. It's responsible for everything from the light we see to the electricity that powers our homes. Just like gravity, electromagnetism isn't a force that acts magically at a distance. It arises from something called a field, an invisible influence that permeates space. Imagine a magnet attracting iron filings. The filings aren't being pulled directly by the magnet, they are responding to the magnet's magnetic field. This field concept is crucial for understanding how forces work. In the case of electromagnetism, charged particles create electric and magnetic fields around them. These fields in turn influence other charged particles, causing them to attract or repel each other. We've explored how gravity pulls objects together, but what if gravity could push objects apart? This concept, often referred to as negative gravity, sounds like something straight out of science fiction. However, it has a basis in modern physics theories. Negative gravity isn't about flipping a switch and making gravity repulsive. Instead, it relates to the idea of exotic matter and dark energy. Exotic matter is a hypothetical concept involving particles that have negative mass. If such particles exist, they would produce a gravitational effect opposite to that of normal matter, potentially pushing objects away instead of pulling them together. Dark energy, on the other hand, is a mysterious force driving the accelerated expansion of the universe. Some scientists theorize that it could be a form of negative gravity, counteracting the attractive force of normal gravity on a cosmic scale. Have you ever wondered if gravity affects time? According to Einstein's theory of general relativity, the answer is a resounding yes. Gravity doesn't just pull on objects, it also warps the very fabric of space and time. Imagine space-time as a flexible sheet. A massive object like a planet or star creates a dent in this sheet, causing it to curve. This curvature affects how objects move, but it also influences how time flows. Closer to a massive object where the gravitational pull is stronger, time actually runs slower. This phenomenon is known as gravitational time dilation. For instance, a clock placed near a massive body like Earth will tick more slowly compared to a clock far away in space. This isn't just a theoretical concept, it's been confirmed through experiments involving highly accurate atomic clocks. It means that time is not a constant, universal flow. Instead, it's a variable experience influenced by gravity. Physicists have long sought to unify the fundamental forces to find a single, elegant theory that could explain all four forces as different manifestations of a single underlying force. This quest for unification has led to groundbreaking discoveries and continues to drive research in theoretical physics. One successful unification came with the Standard Model of particle physics, which successfully unified the electromagnetic, weak, and strong forces. This model has been incredibly successful in predicting and explaining a wide range of particle interactions. However, gravity remains the outlier, the force that has yet to be fully integrated into a unified theory.